In the last lecture, we started the effect of time varying magnetic field, and we realized that whenever the B changes with time, it induces an electric field, and that electric field can be calculated if the field is symmetrically configured. So, in case of cylindrical region and a uniform field or symmetrical field, we can calculate the value of E. But in general, it is difficult to calculate it. Okay, the calculation is only meant for the uniform and symmetrical magnetic field. It should be, I mean, it could be non-uniform, but it should be at least symmetrical. The symmetricity is important. And the symmetricity which we expect is only cylindrical symmetricity. So only for cylindrical symmetricity we can calculate the E. For other symmetry we cannot calculate. So we are considering a region in which B is constant. Let's say the radius is A, or we can take R. And the B is varying. I'm considering it to be positive. Okay. So there are two formulas that we derived. The E inside and the E outside. So for any point which is inside the region, the E turns out to be how much? The E turns out to be
R by 2 dB by dt.
Yeah, very good. But the moment you go beyond this, it becomes
capital R square by 2R dB by dt.
excellent. So these are two formulas, and using this we can find a lot of other derivations. So let's say we have a rod. So first of all, we do have a cylindrical field. And now we have a rod. So a thin rod of length L is kept in such a way that the perpendicular distance from the center is D and the length of the rod is L. Okay. And what is given to us that dV by dt is positive. Okay. Now, if dV by dt is positive, then what you can realize that every point of this rod is having different distance from the center.
Yes.
So we can say that the E, first of all, this rod is luckily within the field. So the formula that will be applicable is the upper one.
Yes.
And the second is that the point O and the different points of the rod, that is the center of the cylindrical region and different location of the rod, will have different R values. Okay. So we don't have the same R, we have different R. So if we have a, if we take an elementary, let's say if I take a small piece of this rod, which is located at a distance R from the center. No, I'm taking R from the center because I should have the formula to write. I have a formula to write E as a function of R. So I have taken R, which is the distance of the elementary, and I'm also taking some other variable, let's say X, theta, and I'll call this length as dx. Now, if dv by dt is positive, which means the inward field is growing with time. So if I hypothetically assume a ring passing through the elementary, what will be the direction of induced current in that ring? So if you
It
draw,
is perpendicular to R.
correct, very good. If you draw a concentric ring, so the B value, the direction of B will be, so the direction of E will be in this sense. Okay, it's not visible. Let me make it visible. Sorry. So now this electric field is in this direction. Now what we are trying to find is, we're trying to find the induced EMF in this rod. The calculation of induced EMF in the rod. So now we have to go through the basic definition of EMF, that D equals to, we know that it is E dot DL, right?
Yes.
So you can see the E, if I take this as theta, this is 90, this is also theta.
Yes.
So the component of electric field along the rod will develop the induced EMF, right?
Yes.
So it is E cos theta multiplied by dx, right? We can write like this.
Yes.
And now we can substitute the value of E, which we know already. So the dV or dE, whatever. And the formula for R, E we can write as R by 2 dy dt cos theta dx, and therefore this will become dV by dt 1 by 2. And R cos theta is how much? If you look
R
carefully,
cos
R
theta is D.
exactly. So I'll substitute the next step. So what is interesting here is that this only depends on dx. I mean,
Yes.
everything is constant like. And now to find the net induced EMF in the rod. So E across rod we can write as d by 2 d by dt, and dx integration will give you how much?
So,
Okay. The L, the length
I mean
of the,
yes.
so we can write as L d by 2. ठीक है, कल कितने जाओगे? So now what we can realize from this formula? So finally we got the answer. And what we realized from the formula that the induced EMF in the rod, it depends on the distance from the center, the perpendicular distance, right?
Yes.
So if you have a rod which passes through the center, what will happen? It cannot have the induced EMF, right? So at the D 0, the E rod will be also 0. Because you cannot change L, you cannot change d by dt because both are there, but you can change d. And interestingly, for a d 0, it means if the rod itself crossing the center of the cylindrical region, in that case, and we also understand the logic, so that logic is pretty much simple. Now there is, I mean, such rod cannot have the induced EMF. If a rod passing through center, it cannot have the induced EMF. The reason is simple, because if you choose any point, the direction of field will be either up or down, isn't it? Because every point is on the diameter, no?
Yes.
So from center, if you choose any point on the rod, it will be always like tangential, right? Like this.
Yes.
The the angle of dx, or you can say the rod and the field, will be mutually perpendicular, and therefore the E cannot have a component along the rod. Okay, so E parallel will be 0. Okay, this is like E perpendicular, and there is no parallel component which can contribute to the EMF, isn't it?
Yes.
So now, do we need to do this rigorous calculation to get the answer? The answer is no. You can do it very easily. So the method 2 is pretty easy. So I gave you a question like this, right? So the rod. So you can draw, or you can imagine a a rod touching the edges and center. So you can make a closed loop, and this closed loop is like a triangle. So the flux through the loop is how much? B into half LD, base into height.
Yes.
And now d phi by dt becomes LD by 2, and this is the answer to the rod. Why? Because the other parts, A and B, OA and OB, cannot have the EMF. So the net EMF of the loop is actually the EMF of the rod. Understood? Is this clear?
Yes.
Just a minute. Sorry. So you understood this how this is done? So
Yes, sir.
the P in the rod we can write as LD by 2. And why we are saying this is rod? Because the other two parts, the OA and OB, even if we assume some rod or some connecting loop is present, those two will not contribute in EMA. So although we are finding for the loop, but we can say this answer belongs to the rod itself. Okay. So this idea can apply anywhere. So you can apply for the outer part also. So imagine, oh, sorry. Imagine if we have a okay, what I'll do is I will not draw the cross and cross. This is the cross field. So let's understand this part. I'll do just only one cross.
Can you just come back in a minute?
Yeah, sure. Okay. So now we have a rod which is outside, as you can see, and the angle that the rod will subtend at the center is alpha. This length is L. Okay. So now again, let's say d by dt is positive. So radius of the this cylindrical region is r. Okay. So no matter how far the rod is, no matter how far the rod is, no matter, okay, this is confusing. So radius is basically up to here. You might think, okay, that is the radius. Right. Okay. But if you look at the flux part, the flux is only from this part, correct? So we have very much confined part of in which the flux will be there. Now it really doesn't matter how far the rod is and how big the rod is. Once you fix the alpha, the flux gets constant, isn't it? Is this clear?
Yes, sir.
So therefore, the flux we can write here is half R square alpha into B, right? Which is the sector area. And any rod which passes the center cannot have the induced EMF, whether it is inside or outside, doesn't matter. So therefore, the d phi by v dt we can write as so the magnitude of induced EMF in the rod. Is this clear?
Yes.
So for outer rod, you know, this is simple. And if we have a rod which is extending from inside to outside, then you have to do the calculation separately. That is, for example, if I give you the example of this is a mistake. So imagine if you have a rod like this. No, this is also easy. This is different, but you can create another question. Okay, let's do this question. So let's say what is given to you. This is the radius r and the length is L given, and this is touching tangentially. If dV by dt is positive, can you tell me what is the induced EMF across N? And also, can you tell me which one is at high potential, A or B? So which end is at high potential? And what is interesting here that in case of induced electric field, if you remember the derivation, the E dot dl, if this is positive, it means it will grow in value. So the potential difference is actually positive E dot dl. Earlier it used to be minus.
Sir, B is at high potential.
Yeah, B is at high potential. In electrostatics, and what we need to know that the E in the two cases are quite different. So this E is called because you see this E having origin not associated with charge. This E having origin associated with charge. So one field is due to charge, other is without charge. Because you can see in this diagram, do we have any charge? No.
So,
So we do have electric field without any charge, isn't it?
yes, sir.
So it is like a person is born without having any parent or mother. What do we call? In mythology, we call avatar, avatar. You know avatar? Avatar,
Not sure, sir.
not sure. You have seen the movie Avatar?
Yes, sir.
The avatar means someone who has come from nowhere,
Oh,
like from sent by the god directly. It's like that.
okay, sir.
Like you might be knowing from mythology, the Vishnu Avatara.
Oh, I thought like it meant form or something.
No, no. So Vishnu is not born out of some mother, right? So Vishnu just came from the. It's like the god descent of God.
Okay, sir.
So this E is born without a charge, which is the our one. So this is called non-conservative electric field. But this is called
Conservative electric.
conservative field will begin from positive and will terminate to minus. Non-conservative don't have the beginning or end, they always make a loop.
Sir, so like this field is more like a spiral, but then it's so close that it's like a concentric loop.
Yeah, I mean, yes, you can call it. So the field of non-conservative field will form a closed path. But in the field of electrostatic field will never form a closed path, rather it will have the beginning and the termination.
Okay, sir. Yes, sir.
The
Sir, this
beginning,
non-conservative electric field, we have like based this upon the behavior of a conductor inside the solenoid.
no. Non-conservative field is the field, yeah, which is due to the only time varying magnetic field. Yeah, what you're saying is indirectly correct. You're saying that in a solenoid, if I vary the current, then it will create a field which is non-conservative electric field. That's correct.
Okay, sir.
Now, see, the origin may be different, but the action, the behavior will be same. So if it is a field, it will apply force on charge. That is always true. The only thing which is mysterious here is that the way it is came into being actually.
Yes,
So
sir.
the mechanism is different, and generally, in general, the case that we have studied so far, that only we know that uh, only charge produces electric field. Okay. But right now we are in a different situation. We have a electric field not produced by charge. So even if I remove the rod, field will be there. Field will be there as a concentric circle. And because here we have the cylindrical symmetricity, so it will have, so we will have a concentric circle as a electric field lines. Okay. So what we will have is a vortex. So we have circle, we have circle, we have circle, we have circle, and you can draw arrow to each circle. So these, if you do, if you draw a tangent, then this is representing the electric field in the space actually. Okay. So why I wrote these two formulas? Because this is something unique, and here the potential in every loop will keep on adding up. So if you have n turns of a loop kept there, and if you start moving from one end of the wire, and if you make n turns and come out of the wire, the E dot dl will keep on adding. It will never subtract. So one rotation is 2 pi r, so two rotation becomes 2 times, and that is 4 pi r. Three rotation becomes 6 pi r. So n rotation becomes n times 2 pi r. Okay. So that means every loop will have its own value of EMFs, and all will add up. So the n loop, if I draw n loop, n concentric loop having same center, overlapping loop, not. So if I have n overlapping loop, then all will have same EMF, and therefore if you have n turns, it will add up n times. So what is the takeaway here? The takeaway is the potential will grow in the direction of field amps. So what you said is correct, because if you resolve the electric field value at any point on the rod, the component is towards B, right? So when you go from A to B, the potential will add up. So you start with A and you add E dx something, E parallel dx, E parallel dx, and eventually you reach the point B. So you're adding the potential to reach the other end B. Okay. So A to B will be, I mean, in case of A, in this situation when dV by dt is positive, the B will be at high potential. That's correct. So to understand which one is at high potential, you can choose any element. And then just check the electric field at that point. So definitely the E parallel is facing towards B, right? And that is sufficient for you to understand at which end is going to be high potential.
Yes.
Understood? So the way of writing is VA, because you can see the direction. So VA plus E parallel dx, that's what, from let's say 0 to L, that will give you VB. So VB is always more than VA. So you can say this implies VA or VB. So the behavior is quite different from the electrostatic behavior, because the word electrostatic is meant for static charges, and we don't have any charge at all here. So this concept of field here has nothing to do with the electrostatic, and therefore it will follow its own rule, and we need to worry about it. Okay, understood?
Yes, sir.
All right. Next. Now we can talk about a circuit. Imagine we have a cylindrical region the way we discussed so far. Okay. So now imagine if I draw a circuit. This is the center. So the circuit will have it's a square loop, and the center is at the center of the side of the loop. So one of the side is the center. The center of the side of the square loop is also the center. The side length is A. So total resistance of loop is R1. So each loop, each side will have how much resistance? If R ohm is the total resistance of the loop, then what is the resistance of each part, each side?
R by 4.
R by 4. Now imagine the d by dt is positive. You could have taken negative. So now which side will have no EMF?
Sir, the one that coincides with the ohms.
Correct. So you can draw, let me make it a number it or name it. So AB will have no EMF, so AB will act as just a resistor of value R4. Okay. Now BC will have resistance R4, but BC is not passing through the center. How far it is from center?
So it is.
Pardon?
Sir, BC, how far it is from the center means from point C, sir.
Point O. Like BC is the length, na? It's the rod.
Yes.
So what is the perpendicular distance of the rod from the center?
Oh, sir, A by 2.
A by. So what is the EMF induced in the rod? If you remember the formula, or even if you don't remember, you can make a triangle and get the answer quickly or mentally. So if you think of this triangle made by the center B and C, it's the triangle of side A and A by 2 as perpendicular side. So area will be how much? A square by 4.
Yes.
So area into d by dt is the EMF induced, right?
Yes.
Now the only problem is which end is at high potential, B or C?
Sir, C is at high potential.
Correct. So C is at high potential. Just a minute. No, C, no, not C. I think it will be
Yes, sir, B
B.
is at high potential.
B is the high potential. So you have to replace this length by the EMF by a cell, and the value of the E will be the E1 will be A square by 4 d by dt. Do you realize this?
Yes.
Now similar, because the AD is similar, and now which one is at high potential?
Sir, D.
D. And what about the DC? DC will have R by 4, but it will also have the EMF induced. And the distance of DC from the center is,
Sir, it's A.
it's A only, right? So the answer is A square by 2, right?
Yes.
And which one is it high potential? C.
Yes.
So the answer will be the, let's call E2. E2 will be how much? A square by 2 d by dt, right?
Yes.
And if you add all the three value E1, E2, E1, you can see all these support each other.
Yes.
And that is called the net EMF, which is we can easily find using the Faraday law directly. So the E net in the loop is how much?
A squared dV by dt.
Which is obvious, no? If you add E1, E2, and E1, you get the same answer.
Yes.
Okay. But now this is to understand that okay, how we can convert a given circuit diagram into a proper circuit, and then we can answer all the conceptual question if they ask. So the first question is what is the potential difference? Now look at this question. This question is very tricky one. I'm not asking the EMF induced. I'm asking the potential difference of A and B. So first of all, let's find the I induced. So what is I induced? Tell me.
E is by R.
So it is E net by R, right?
Yes.
Okay, fine. That's okay. So now current will flow in which direction? Like anti-clockwise, correct?
Yes.
So what is the potential difference between A and B? So you can see when you have a current, then in the direction of current, potential will decrease. So now you can write the VB at high potential. So VB minus VA will be IR by 4, correct?
Yes.
And IR is basically the E net. It is E net by 4,
Yes.
correct? But if I ask you what is now VA minus VD, so it is IR by 4 VA plus VD, so minus E1, correct?
Yes.
So E1 is how much? It is E net by 4, and this is E net by 2. Am I right?
Yes.
So the IR is E net by 4. Sorry, IR is E net. So this is, and E1 is also E net by 4.
Yes.
Now, what is interesting? If you bring a circuit, then circuit will take the EMF as a source, and when it comes to the potential difference, we define for the circuit. So circuit will have potential difference. You can see that VA and VD are having same potential, and therefore we should not have any doubt that VB and VC is also going to be have same potential difference. Okay. So if you go from C to D, then VC plus E1 minus IR for IR by 4 equals to VB, and so we'll get the zero answer. What about the DC? So DC will give you some answer. How much? Can you
So
guess?
how will there be no potential difference and how will there be current? So
No, this is the potential. EMF is the driving the current in the circuit, and luckily the 2 points. See, it is like you are into some magical reason in which someone is driving you externally, which you don't see. Okay, and when we are saying the potential difference, then we are finding the potential difference of the circuit, not of the space. So because of the applied field, you're coming down, so the IR value and the EMF value is cancelling each other. So potential difference is zero. So it is like, you can think this way. If you have
So
a,
initially
if you have a,
not
if yeah, if you have like something like this, you climb the mountain. This is the branch. Let's say this is branch A to D. You climb the mountain, but IR will let you fall. So eventually you are at the same level. No? Understood? Like this. E1 is raising you, but IR4 is letting you down. So potential wise, A and D are same. Understood?
yes.
Potential we are finding for the circuit. The EMF is what you get from the space. Okay. And then we are calculating both. So potential difference is different from the EMF induced part. In the EMF induced, we don't consider circuit. The EMF induced is part for the length. So if you give me a length, I can tell you what is the EMF in that length. If you give me a loop, I can tell you what is the EMF in the loop. If you give me two loop, I can tell you what is the EMF in the two loop. So EMF is like a, you can think this way. Let's say, have you eaten jalebi?
Yes, sir.
So imagine that jalebi is the circuit. Jalebi is the fried jalebi. It is now still to be dipped in the sugar syrup. So before it is dipped in the sugar syrup, jalebi will have only circuit. Understood? The moment you dip, the sugar syrup will get inside, and that will bring the taste, isn't it? The sweetness.
Yes, sir.
So circuit is like the dry jalebi which you put into this immersive electric field, and that field becomes like a syrup which passes through the jalebi, and that will drive the circuit.
Right.
Okay.
So like the EMF is associated with the space, but then
Yeah,
the resistance is associated with the circuit.
exactly. Now you got it.
Yes.
EMF is the property of space, and you can be the beneficiary of that spatial property. So by being there physically, you can also take the advantage of that field. Now the person who is trying to maintain that field is doing some work, so it is providing you the energy to do the work. Okay, so circuit is deriving energy from the external source because you're trying to destroy that electric field, but the one who is maintaining it externally, maybe the solenoid current in the solenoid and so on. So the agent who is trying to maintain the dE by dt value, that person has to do some work externally, and that agent's energy become part of the circuit energy, and in a way the electrical dissipation will come from the invisible agent which you don't see, because see, energy should come from somewhere. Now I am not the creator of energy. I don't have a cell attached to me physically. I am making the use of the spatial voltage or spatial field present. But the moment I make the use of it, I consume that energy. So in a way, I'm going to change the dE by dt value, but someone is trying to maintain it externally, and therefore that guy is giving me or doing some work in maintaining it, and that energy I'm receiving it. Yeah. So the the electrical energy actually come inside the circuit in form of electromagnetic waves. So we'll come to know later on that the electrical energy is received in EM waveform, the electromagnetic waveform. So I square R is also EM wave energy, or you can say electromagnetic energy. I square R, yeah, the power which we write. But that's a different perspective of looking at it. Okay. So I square R will be also
Magnetic wave energy.
yeah. I square R is also electromagnetic energy. That's very strange, and I would say counterintuitive, but that's the reality. Okay.
Okay.
So from D to C, we get some potential. So I can add VD minus VC equals to minus IR by 4 plus E2. But this time it is minus E net by 4, but plus E net by 2. So the last answer is E net by 4. Now, if you look carefully, we got this value initially in the B and A part, and then this value VD and DC. Okay. So the potential difference and EMF induced are two different aspects. So I mean, the question setter should ask that find the potential difference between the point A and point B of the circuit. I mean, they have to mention this explicitly. Understood?
Yes.
Okay. Anyway. So now there is a very famous question based on this idea. Imagine we have a small cylindrical region of radius small a having uniform magnetic field B. Okay. So the B is uniform. What we have is I have an insulating ring. Imagine this ring is kept on a table and there is a hole in the table through which I have a solenoid. And what you're looking is the top view. So this ring is kept on a frictionless table. This is the top view. So this a ring of radius B is kept on a frictionless table. So a ring of radius B is kept on a frictionless table. Concentric with the magnetic field region as shown in the figure. Okay. Now, what is the question? The outer ring is given some charge Q. So this is insulating. Okay, the charge is Q. The radius is B. Let's make it B. And there's no, see, it's not d by dt given to you directly. You have to think that okay, this will come as an indirect question. Find the final angular velocity of ring after the field is switched off. The ring is having mass m. So the moment you switch off the B, what will happen? See, nothing will switch off in 0 time. It will take some time, maybe dt time. So the value of B will go from B value to 0 value, right? This is B naught. So what is the field now? The present field is how much? The present field is B naught. Okay.
Yes.
And the moment you switch off, it will go to 0 value. So although we don't realize this in general, but there is a d by dt term coming inherently because B is changing from some value to 0 value. So there is a differential change happening. If I take that interval as some time and if we divide that into small pieces, our B is changing from some finite value to 0 value. So the obvious question is, in that small duration, because the dv by dt is very high, can you imagine dv by dt? B not to 0. When you switch on, switch off something, it is a rapid, I mean, action. It's very rapid, right? So the d by dt is like infinite value, right?
Yes, sir.
So this creates impulsive electric field. You know, impulsive. The E becomes really large in value.
Yes, sir.
And this impulsive field in no time will create the impulsive torque on the ring.
Yes, sir.
And that impulsive torque will create the impulsive acceleration, and that impulsive acceleration will create omega in no time. So what you have to think is, okay, you don't think this is impulsive or non-impulsive. You think that, okay, this is the process of d by dt. Think of how to write the differential equation to get torque, and from torque you can get the I alpha, and from I alpha you can get the omega. Can you try this now?
Yes.
Yeah, try this now.
Sir,
You got the answer?
sir, I'm getting QR square B naught by 2 MR square.
The R should not come. No?
Sir, the angular velocity.
Ah, so we have A and B as ready, guys.
Yes.
Yeah. So maybe we can
Sir,
change
that
R to
means
B.
QB square B naught by 2MA square. No. One second, sir. I'll just A square. So
Maybe
it's QA square B naught by 2MB square.
like that. Let me see. So Q into E is I alpha, right?
So Q into E is a force.
Into a
right?
B. Q into B.
Yes.
And this will become how much? A square by 2B.
Yes.
So now this is obvious. What you got is right. Okay, this B cancel. So Q A square by 2 dB equals to MB squared omega, and then the B will go from B naught to 0 and omega 0 to omega. So in the formula of E, we can write minus sign. I mean, E equals to minus if you write the value, because the d by dt is negative, na? So we can make it minus here to make it positive, right?
Yes.
Just we are writing value. So anyway, this will give you the answer QA square by 2B naught equals to MB square. And omega turns out to be okay. So this is a very typical question and very famous. We should know this question. And this is from NCERT. No?
Yes.
So I think we are done. We can just see if we can add something more. Or else we can go to the next concept. Yes. So now once you get the omega, you can ask answer many questions. So what is the find magnetic dipole moment of loop? So magnetic dipole moment is what formula? NIA. So we can say I into A, and here I becomes I molecular, right? Because it's a rotating loop, so we can write as I molecular into area, and I we can write as Q omega by 2 pi. Area is pi b square. Pi b square. So answer is Q b square by 2 into omega, but omega we got itself something else. Q a square b not by. So we are getting answers Q a Q square a square b not by 4m, right?
Yes.
But once the loop is in rotation, it itself is the source of current, right? So the third question I can ask is, the third question we can ask is, Find the final value of B at the center of loop. So now see, once you switch off, that B has gone. Okay. But now the rotating loop itself is the source of B. And then we know the answer for the rotating charge. So we can write as mu naught I by 2R, right? So for any current carrying loop, what is the magnetic field at the center? Mu naught I by 2R.
Yes.
Do you remember?
Yes.
Okay. And the molecular current we write as Q omega by 2 pi. So it is mu naught by 4 pi Q by B into again omega, and omega is Q A square B naught, Q A square B naught by how much? 2 MB square. So nothing gets cancelled. That's fine. 8 MB power 4 the final B is this much. So they may ask you what is the ratio of final B and the initial B. That's very interesting question. Huh? So once you switch off, you have some other way to get the B at the center. And okay, this looks conclusive. Okay. It is clear?
Yes.
Now. Okay. Fine. So we can go to a question of solenoid. So let's say we have a solenoid. So Imagine if I connect a solenoid with a source and the source voltage varies with the formula V naught sine omega t, or you can say omega naught t if you want to keep it different from omega. So now the B will be, now if this is the value, let's say let R be the resistance of wire solenoid, or we can say, so if R be the resistance of solenoid wire, pardon?
So can you just come back in a minute?
Yeah, sure. Yes.
Yes.
So now, if I look at the current value, if we talk about the current here, and we are finding the current through the wire, so the V value, or you can say current value, will be, let's say, V by R, and although this is not correct because the solenoid will also have the back EMF, so I'm trying to create a question actually, so this question will not work. Okay. Okay, so imagine if V is sinusoidal, then current will be also variable, right? So current will also have some function of time t, right?
Yes.
And because V depends on current, so we can say as current will change. We have done this before, but we are trying to use this in a different context. This is the d by dt condition, and if I bring a ring here, concentric with the axis of solenoid, and if this ring is given some charge, okay, I should have taken simple as well. Let's say not. It's not a charge. Okay, what I'm trying to solve is easy to solve without this assumption. Okay. Yeah, I got it. So imagine there is a DC source, there is a switch. And the resistance is R. Now, once you switch on, what will happen? The B will go from 0 to some value. So the final current in the loop will be how much? Because eventually what will happen? The final current will, this entire circuit will act as uh, a current carrying loop with the resistance R. So the final current is going to be V by R. So you can see that the current has gone from 0 to I final. So we can say the B value, the current is going this way, and the B value will also go in a similar fashion from 0 to mu naught in I final, right? Isn't it? So in the switching on process, we can understand that there was a d by dt term inherent. Do we realize that there's a d by dt?
Yes,
Because
sir.
b is constantly changing from 0 to some value. So there is a d by dt term, and therefore in that duration, you will have an electric field induction. And there is an induced electric field, the non-conservative one. And therefore, if I have a concentric ring with some charge, and this is the gravity free space. Because you may ask how the ring will hang in the air. So that's why I said, let's say, assume it's gravity free space. The ring is very much hanging in the air. And once you switch on, the ring will experience the torque and it will start rotating, isn't it? Understood?
So are you able to hear me?
Yeah, I can hear you. Can you hear me?
Yes, sir.
So do you realize that during the switch on process, the similar thing will happen? The ring will experience the torque due to the induced electric field,
Yes, sir.
and so it will attain the omega.
Yes.
So here the B will go from 0 to B naught and omega will go from 0 to omega naught. Okay.
Yes, sir.
So you can take mass of the ring as smaller and then you can add the answer. So what you can add? So QE, okay, I need to give something more. R equals to I alpha and then we can get that. This is E is R by 2 D by dt. I is mi square by 2
Sir, it's a ring, right, sir?
Ah, my bad. It is mi square into alpha, correct?
Yes, sir.
So the r square gets cancelled out here, right? Because
Yes.
so q by 2 dv by dt is m d omega by dt. So q by 2m and now you can integrate. So 0 to b naught and this is 0 to omega. So the answer we are going to get is so q by 2m into b naught is omega, right? Yeah. Fine. This is very nice answer, right? QB naught by 2m. So we have seen QB by m called omega, but now it's QB naught by 2m. So the ring will attain this angular velocity. So dE by dt can come in various forms. So switch on, switch off is one of the very popular form in which question is designed in the examination. So the moment you read a question with switch on or switch off event of magnetic field, you should understand that this question is belonging to dE by dt question. And once this will click, you will be able to solve the question. Okay. So it won't be difficult for you if you understand that simple part. Is this clear?
Yes, sir.
Okay. So I think we are done with the first part of EMI. I mean, the variation part, and now we are going to learn other part of EMI chapter, which is mostly about circuits. So where we use the idea of Faraday's law, of course, but in a slightly different manner. Okay. So the next topic of discussion is mutual induction. So shall we start in the next lecture? That's okay.
Okay, sir.
Okay. So I'll start the mutual and self and try to finish at once. And also it's good for me to post on a channel. So okay, we are meeting on Thursday, right?
Yes.
Yeah. Fine. See you on Thursday.
Yes, sir. Bye, sir. Thank you,
Bye.
sir. Sir, and yesterday you had forwarded only yesterday's PPT, sir.
Okay. Yesterday I have forwarded the PPT. You don't have?
Sir, the other PPT, I guess the one before yesterday.
Okay. Okay. That one. Okay. Yeah. Yeah. Fine. Fine. I'll send you that one. Yeah. Sure.
Okay.